So, gentlemen, my name is Engineer Uche, and today I will be taking with the resource person for the training. My colleague will join me for the road design later on, but I will be taking you on the water reticulation urban design training. So my background is civil engineering. I attended the Federal University of Technology, Owerri, where I studied civil engineering for my first degree. After then, I proceeded to University of Stuttgart, where I did water resource engineering. Now, this training now have been going on for the past 3 years, and it's wonderful. The turnout has been massive. But due to COVID, we now decided to make it a weekend course. So this is cohort 2. In cohort 1, we had about 25 individuals who we believe were trained to become infrastructure experts. I'm aware that you won't become an infrastructure expert overnight, but it's always good that somebody gives you a head up, that somebody gives you a whole lot of materials. I remember the day I graduated after my master's degree at Stuttgart. Okay, we are so excited and we are so happy that we are graduated, we are going back to our country and all those stuff. And one of the lecturers walked up to us and said, "We've really not taught you anything, but we've shown you what you should know." And that what got me thinking that most times when you come for training like this, that will not transform you into an expert overnight. But the tools that you need that will make you an expert will be given to you. And that's exactly what I'm going to do in this class. We're going to learn. I'm going to learn from some of us, and some of us are going to learn from me. As I always tell people, it's all about perspective. I learn from your own perspective, you learn from my own perspective. Nobody's perspective is perfect. Okay, so being in this class today, having that confidence to register and make payment is because you believe you want to learn a new perspective. Okay, you want to learn how it is being done outside the shores of this country and from a different entity, and that is quite cool if that will be your mindset. And that's exactly the mindset I want you to have. In terms of water demand calculation, in terms of urban designs, I'm going to give you top-notch training, and you're going to get it, right? Just stay with me. All I ask of you is that after this training, find time to go through the materials, find time to watch the videos. And if there are issues, if there are questions, if there are things you don't understand, you come to the next class and ask me those questions. Right. Now, looking at the material, this is the folder you have now. If you open this folder, it has a lot of stuff inside it. But I'll just tell you some of the things, okay? We have materials we're going to read from chapter 1 to chapter 8. Right? I needed you to read those materials, but I'll just glance through some of them. Then we have a case study called branch system. We're going to treat this case study because of the classes. Then we have what I call nomogram. These are charts for pipe sizing. I'll teach you how to do that. When you want to, after you've gotten your discharge, the water demand, you needed the pipe, size of pipe that will be able to successfully conduct that volume of water. This is the 3 charts you use. There are 3 because they have different roughness, okay? One is for concrete, one is for ductile iron, one is for PVC pipes. So depending on the material you're using for your water reticulation, you use the appropriate, the right type of chart for that. Then here, I'm going to make a presentation, and this is where we're going to start. After the presentation, I will now show you, in the course of the presentation, I'll show you about water quality requirements, drinking water quality requirements based on German standard, WHO, European standard, and WHO standard. So these materials are all here for you, and videos will follow shortly. Now, I'm going to give us a presentation to start with, and that is this slide, presentation and overview of centralized water supply system. If you don't mind, I would like you to open it. I love to start with this slide because this is a presentation I made many years ago when I came back from Germany, and I was asked to make a presentation to the Nigerian Institution of Water Engineers. So I made that presentation, and each time I'm doing training, I would like to fall back on that presentation. The reason being that the presentation summarized everything you need to know in one PowerPoint in order to design a centralized water supply system. Okay, today is the starting day. Some people will call in and okay, I'm sorry about that. I think one or two of us are having issues logging in. So can we open this slide? Design of water supply for a case study. Okay. Just hold on, gentlemen. Some of us are having issues joining this meeting and okay, meeting info. Copy the link. Just hold on, please. Can somebody see if I'm sharing the slide? I've already shared the slide. The slide is already on Google. Okay, so this is a summary. Let me start with a summary of how you go about water reticulation, either from the angle of a consultant or from the angle of a contractor. So this is what you need. If you are asked to, we'll start from the angle of a consultant, okay? Because you are the infrastructure expert and you've been consulted and be requested to design a water reticulation system, okay? So the first thing you do is there are 6 components, or 5 technically. You do the introduction, you do the description of calculation basis, you do the presentation of estimated figures, you design your distribution network, you analyze the distribution network, and then you conclude on your design. In the introduction, for you to design a water reticulation system, you need a map, you need a layout, you need topography. So that's the first thing you need, okay? There must be a map, there must be a layout. If it's an estate, the architect or the urban planner must have given you a layout showing the distribution of houses, low density area, high density area, and what have you, right? So after you have those maps, then you now write a description of the area. Okay, so then after that, just hold on, gentlemen. Hold on. Hello? So the next thing you do is, after you have done your population growth, future development, you now present those figures and compute your water demand for each catchment, for each section, for each subgroup, right? And then after that, you now design your distribution network. After designing your distribution network, you now analyze it to make sure that all the standards and all the parameters are met. So shortly, this is what I mean. So the first thing is, for this case study now, this is the city you want to design. So you do an introduction. Where are the sources of water? What are the unique features of that place? You state it in form of a report. There's a report that goes with this design. I will share a template with us. The next thing is that you define your objective. What are you designing for? For this case study design, we are designing for a water supply system in accordance with approved engineering and quantity requirements to meet the water demand of Wildkersheim. That's the name of the city we designed. Okay. We now say we're taking a pessimistic view of population growth. In other words, we are not too positive that the population will just explode. Rather, we're taking an optimistic view on the industrial sector. This design was done in a city in Germany. So then their industry are growing, but their population was going down. Then the other thing is that we have wide range of water demand users. If you are designing for an estate, it is purely residential, so it's defined. But if you are designing for a place like Abuja or Lagos, then there will be industrial estates, there will be layouts, there will be residential areas, there will be schools, there will be recreation ground, there will be this, there will be that. So you need to capture all those things, because when you are designing them, you must determine their water demand sectorally. So what next you do? You now study the area. You describe the area. How is the area? What are the contributing streams in the area? How is the geotechnique of the area? How is the groundwater flow, if you have access to this information? And are there danger spots? Are there landfills? Are there mining areas that you should avoid? Or are there, you just give a total description of the place you are designing for. The next thing is you describe the sectoral, you give a sectoral study, okay? Like if I'm designing for a place like Abuja, I'll say that Wuse area is a commercial area, Central area is a commercial area, okay? I'll say that Lugbe is a residential area. I'll say that Pape is a mining area, Kubwa is, I'll just give a total description so that your client or whoever is reading your report will be on the same page with you in terms of understanding the dynamics or the unique characteristics of the area you are designing. After that, you include some pictures of the place, get some maps from Google Map, GIS person, surveyor, architects, plan, just get some information that will enable you to have a background, know how to do your distribution and your network. Okay, you can also do come up with how the area is undulating, okay, in terms of the how the landscape is. It also has a way of making you understand. The next, making people to understand how the area is. The next thing you need to do is you might have to take sections. You have to cut sections and show why you need to provide 2 water systems. Now, looking at this picture, you could see that it is not easy to have just 1 water system for this area. It's almost impossible, because I'm wondering how you can lay your pipe along this valley. So if this is given to you to design, you definitely tell your client that you're going to do a decentralized water supply systems. You can still call it decentralized systems, but that means it will be phase 1, phase 2, or section 1, section 2, right? Yeah, I have a design somebody brought to me some time ago for one medical school in Ogun State, and they were planning to design a centralized water supply system for a 200-hectare land. And this land is almost flat. So there's no much head where you can locate your overhead tank. And when I did this estimation, I found out that the pressure, if you are to deliver water by gravity, the pressure from point A to the last point will almost be 0. So I told them that a centralized water supply system is not feasible, will not work, right? That they need to do a decentralized system. And when I mean decentralized system, It simply means you provide more than one borehole. You provide more than one elevated tank, right? It becomes unit by unit. So if I go to, let's say, Wuse Zone 1, I'll build a system for them. If I go to Wuse Zone 2, I'll build a system. If I go to Ikoyi, I'll build a system. If I go to Lekki, I'll build a system, okay? Not just to locate one tank somewhere and then allow you to distribute, unless you have the head. Abuja is a unique place. Abuja will have only one treatment plant in Abuja, located at Lower Usman Dam. But the beautiful thing is that it has a lot of head. But they also did something like I love that makes it look like a decentralized system. They have like 6 tanks, 6 big massive tanks scattered around Abuja. So when the water from Lower Usman Dam from treatment plant comes, it will go to those tanks. So for instance, Balempa has a tank servicing it. Garki has a tank for himself. Maitama has a tank for itself. So that is how it is. So if you look at the whole system, it is one water source, but a decentralized system. Because centralized system will mean the water will come from Lower Usman Dam and then distribute to all these places, but it will not work. Because some areas, you need to provide booster stations. Some areas, the pressure is going to sub-zero. Therefore, you need a pump to pump it further, right? So you take sections. The next thing you do, and just like what I just explained now, is what we call zoning. There is what we call zoning, pressure zoning. Okay, you can call it zoning or you call it pressure zones. Why do we need the pressure zones? I will tell you why. The standard in water design says that the pressure in your system must not be more than 8 bars, right? The pressure in your system must not be 8 bars. And if you look at in terms of elevation, what is 8 bars in terms of elevation? 8 bars simply means 80-meter height is equivalent to 8 bars. So if I'm doing a design where the difference between the water source and the consumer is more than 8 bars, it means you need to break it into zones, right? You need to break it into zones. It means you need to break it into zones. And when I mean breaking into zones, it means you need to now say phase 1, phase 2, and phase 3. You need to break them into zones, right? You need to break them into zones. So for this design we did, the difference between the highest point and the lowest point is more than 80 meters. So that means what we need to do is to break them into zones. It means we need to break them into zones. And that means we need to specify that all the houses that are within 310 to 270, this is meter above sea level, okay? So it means if your house is falling between this zone, elevation zone, will be serviced by tank 1. If your house is falling between elevation of 270 and 230, you'll be serviced by, we'll call you zone 2, and we'll provide you your own tank. If your house is falling between 300 and 225, we'll call you zone 3. Now, most times you don't need, if the pressure is no more than 88 bars, if it's between 1 bar to let's say 5 bars, you don't need to create 2 zones. It means one elevated tank will serve. All you need to do is to maybe provide a very huge, massive tank, right? Because that tank can conveniently distribute that water to every point without losing pressure. So now, as I said earlier on, you do a background study. When you are doing your design, you must define your design horizon, okay? You need to define your planning horizon. You ask yourself, how long do I want the design to last? 30 years, 40 years, 50 years. When you determine that, you now do your expected growth, your expected development to meet up to the demand of 30 years. What this entails is that you have to project your population to say, what will the population be in 30 years' time? Let's assume that the population for the city is 10,000 people. Now, you will now ask yourself, in the next 30 years, based on the population growth of certain percentage, Nigeria is growing at the rate of 4%. What would the population be in 30 years' time? That is the value you now use for your design, right? I hope we get that very well. Then every other parameters that we will use must be parameters that are tied to that 30 years. So let's assume that they are going to build a university here in 30 years' time. It means you will do your design with the anticipation that there's already a university in that area. The next thing you do is to sample your water source. There are about 4 to 5 water sources. We have the groundwater. Your source of water can be groundwater. Your source of water can be spring water. Your source of water can be surface water. It can be water from a long distance water supply. In other words, from another treating body, like Lower Usman Dam. You have treated the water, and the water is now coming to Kuje or going to wherever. Okay. Then the last one, which have not gotten traction in Africa, is rainwater. So rainwater can also be a source of water. But for now, the cheapest one or the easiest one is the groundwater. Does anyone know the difference between groundwater and spring water? Well, the difference is simply that spring water is already under pressure. So spring water, you don't need energy cost to extract it. For groundwater, you need to pay for energy. But for spring water, the water is already a confined aquifer that's already under pressure. So once you puncture the water, you try to extract the water will come up with a force on its own, right? Then surface water is the most expensive, depending on the level of contamination or the chemical, biological, and the physical property of that water. But you must do your analysis. You must analyze the probable water sources you should use for your infrastructure design, your water design. You must sample them and know which one will suit you more. Then the next thing you do after getting your water source is to look at your population. You now need to look at your population sectorally, right? Now, some of these words are German words, but don't. So if you look at here, you tell yourself, as I'm doing for Abuja, all the areas don't have the same land use. Some areas are densely populated. Areas are not densely populated. Some areas are industrial areas. Some areas are camping parks. Some areas are amusement parks. Some areas are for industries. Some areas are for residential areas. Some areas are for markets. So all these sectors have their unique water demand. So that is why you must take cognizance of their population individually, like a subsector, right? And you also need to project what least population are you expecting and what is the least maximum you're expecting. Engineering is not a science of exactness. We're not exact in engineering. It's more of approximation, right? So that means nobody expects you to guess the population accurately, but at least you must be within some acceptable limits. The next thing you do is that you now project the population of each of those centers for the next 30 years or 50 years, depending on the period you are designing for. The next thing you do is you go and look those water sources and do a test. You need to analyze them so that you know whether it's something you can do or something you cannot do. It's very important that you do water analysis. It will help you to know the kind of treatments required, whether it's a simple filtration system, whether it's nanotechnology, whether it's membrane technology, whether it's reverse osmosis, all these treatment technologies, it is the water quality that will give you an idea. So let me recap what we've said again. We did the background, we did the water quality sources, we sourced the water quality, identified them. We did the population projection and sectoral representation of the population into clusters. Then we did the population projection. We now did the water test analysis. Then we now do the network distribution, right? I think if you look at the slide, that is the progression. Now, when you see diagrams like this, you will discover that what have been designed here are the mains for every pipe distribution network. We have the main pipes, the secondary pipes, and the tertiary pipes, right? The main pipes are the major pipes, the one that goes on the streets, right? Okay. Then we have you can also call it the main pipe, you can also call it the primary pipe, right? Main or primary. Those are the big pipes. In Abuja, the main pipe for Abuja water scheme is about 1,500 millimeters. From 1,500 millimeters, some areas, it moved to 1,200. It started from Lower Usman Dam. It started with 1,500, 1.5 meters. That's the diameter of the pipe. As it gets to somewhere in Maitama, Mogadishu Barracks, it came down to 1.2. Then from 1.2, it came down to around 600. From 600, it came down to 300. From 300, it went to 100. Now, why are they going down? I will show you. Because as the water is moving, the demand becomes more, right? Depending on where you're coming from. So now, the next one is the secondary pipes. The secondary pipes are the ones that tee off from streets. These are the ones that will bring water to your house. No, not to your room, not to your house, but in front of your house, right? Those are the secondary pipes. Then the tertiary pipes are now the one that will bring water into your house. That's the last pipe. So there are 3 levels of pipes. The primary pipe, which is usually very huge, very big, very massive, right? Then you have the secondary pipes, right? The secondary pipes are the one which goes into the substreets, right? Street by street. Then from there, your primary pipe will now take it off. I'll show us an example when it's time. So you could see tank 4 is distributing water to city center, commercial east, and tank 1 is distributing water to Foche and commercial east. Then tank 3 will distribute water to camping ground and industrial north. So you can see that you can call this a centralized water supply system, but it is decentralized in nature, right? There are 4 tanks distributing water based on the elevation of those areas. So because the tanks have to have the highest elevation. So you place the tanks where they will provide maximum pressure to the consumer. Because the most important force is like electricity. The force in the electricity is the voltage, right? So pressure is like voltage. It's the one that pushes the water, it's the one that makes the water available. Now, you can see that after detailing the subgroups or the sub-areas based on their unique composition, you now list their elevation. You now list their population groups. You now list their number of inhabitants. Then you now do 2 scenarios. This is the current scenario. Then in 30 years' time, this will be the scenario. In 30 years' time, this one have reduced by 8%. Why this one have increased by 6%? Housing area have increased by 6%. And the cattle sizes have increased by 2%. So you do this, and then you get the final figure. So if you look at this figure, you see that the figures here are bigger and more. And that is the figure you use to do your pipe sizing. So All these ones are not that very important. They are just part of what a consultant will do. You plot graph to impress. This is more like to impressing your client, okay? You plot the graph showing your client what is the current demand for this area and what will be the future demand. So you can see that some areas are going up, some areas are coming down. Right? Okay, so a recap again. What are the basic steps in water demand, water supply and design distribution? The first thing we said is that you need a map. It could be a layout, it could be a topo map, but it is important that it is a topo map. I didn't just say map, but I said map and topography. Why topography? Because in the area you want to do your water design, you should be able to know the highest area and lowest area, right? Because the water source will most likely be found in the lowest area, while your elevated tank will most likely be located at the highest point. Why do you need the highest point? Because it is distribution by gravity, so that it do not involve energy costs, huge energy costs. 95% of every water reticulation system is always by gravity. So all you need to do is to pump water from your source into the elevated tank, from the elevated tank to come to the final consumer. Then we said the second thing you do is you do a description of your area. Describe the area. Talk about the features of the area, vis-a-vis how you want to source water. Is it groundwater? Is it surface water? Is it aquifer? And so on and so forth. You also describe the area to show areas where it is not good to site the waterborne water, or areas that you suspect might lead to failure. Then what you do next is you now describe your population basis. What is the basis of your calculation, right? What are the water demand users? Schools is different from house is different from industry. Then you ask yourself the second question, are there growth? Is this area going to grow in the future? If it's going to grow, you must factor in the growth in your design. The next one is development. Are there future development? You factor it in. And after you have done that, you now present your values and your figures. When you present your values and your figures, then you now design your distribution network, right? You now design your distribution network and you now do the analysis. After designing your distribution network, you need to come and analyze your network and make sure that all the pressures, the losses, the demand, the pipe sizes, and everything is in order. So that's what we did so far. Any question? So the following slide is just to explain these basic ones. Any question? Should I take no question as we understood everything? Or should I assume that you didn't understand anything?
For me now, there's no questions. It's just a refresher. Sorry for coming late. My name is Musa Titi.
Thank you, sir. Okay, Bukola, your hand is raised. Can you ask question?
Yes, thank you, and good evening, everyone. Right. I have also about 4 questions. So,
okay, go on.
Number 1, I want to suggest that you use a local map, because sometimes when you need to extract information from Google Map, in Nigeria, we might not be able to get it. So when you use a local map, when we have the challenge, we'll be able to know
absolutely.
What option.
Yeah, absolutely.
Can I go on?
Yeah, just hold on. Also, in water reticulation design, the first person that goes to site is your surveyor. You must send your surveyor to site to go and capture the real data. It is only when you are designing a place like, let's say, Sambisa Forest, where you know Boko Haram is there, then you can use Google Map, right? But if you're using Google Map, you must know that there's error. So at the end of the day, you know, just anticipate changes in terms of elevation, because there is about, if not for improvement, unless you're going to go to NASA and get them the real NASA data, okay, Landsat data. But if it is the online Google Map, there will be about a 1 meter difference in terms of your elevation. That's a very good one. Please continue your question.
Okay, so the other question is, you said 80 bar is equals to 80 kilometer.
80
Now,
meters
I see,
height.
yes, 80 meter height.
Yeah.
You might need to expand. For me, I think you need to expand on that because my background is civil, and
Yeah.
I think this play this plays a major role. You sizing your pump. You mentioned pump head. How
Yeah.
do we determine that? Then it also in calculating the demand. I believe it should be scaled down the use. And we have examples of the land use, which could be commercial. The demand of commercial is different from residential, and residential is different from industrial. So
Yeah.
in estimating that, maybe if we are considering heavy industry, for instance, per square meter, this is the standard. And it would be better if it is local data for us to be able to determine. So two things, the head, in calculating the head over a period of a length of area. How do we interpret this 80 bar?
Okay.
Or I think you said 8 bar.
Yeah.
It's equivalent to 80 meter. So the pump head, the daily demand, and the pump sizing. Sorry, the last but not the least, you said the main pipes diameter in Abuja is 1,500.
Yeah, the main one.
I
And
think
it graduated to 1,200 almost immediately after it's exited
yes,
the Warimpa Road.
yes, yes. This is not automatic. I believe it's the sizing of the volume that has been estimated. So my first question cascades into the second, third, and fourth question. Thank you.
Okay. Now, thank you so much. That's a wonderful question. I think what you just did was to move ahead of us. We'll still get there. We're going to do a lot of design. But let me quickly say it here for the benefit of everybody. Okay. The first question is about relationship between elevation and pressure. Right. Now, as is a rule of thumb, my engineer, is a rule of thumb. Okay. In our school, those days we did hydraulics. 10-meter height of water is equivalent to 1 bar. It's just something I know, and I think if you Google it online, it's just what it is. Now, the idea of 8 bars is that we don't want our pipe to burst on the network. Even if some pipes these days can carry 12 or 16 bars, how about the other appurtenances, the other assets? How about the taps in the consumers? So that's why the code I'm using, which is a German code, which we are trying to domesticate to Nigeria through NSC, is to say the maximum pressure we anticipate in our system is 8 bars. So you must not exceed 8 bars, right? If you exceed 8 bars, I'm looking at a scenario where you on your tap, the pressure of water will be so much that the water will be splashing everywhere. That sort of thing. So that is that. Then, coming to the horizontal, that is where pipe losses comes in. Losses comes in, and that's why when you are doing your pipe sizing, you should know whether you're using a PVC pipe, which has a roughness coefficient of 0.1 millimeter. What this means is that for every 1 meter, you are losing about 0.1. For every 1 millimeter, you're losing about 0.1. So this is like telling you, like approximately 10%, let's say. I'll explain this to you later, but not now. Then ductile iron has a roughness coefficient of 0. And then concrete pipes or asbestos pipe, which has been phased out anyway, due to their carcinogenic effect, will give you about 1 to 1.5. So when you are calculating the horizontal losses, it is the function of the roughness of the pipe in addition to the discharge volume, but that one is not too pronounced, right? And then, in fact, generally, losses, which has to be overcome by the pump, are in three things. Those of us who remember our thermodynamics. Losses due to height. Losses due to height is called MGH plus losses due to velocity. You remember that thing we say V square over 2G. Right? Plus the losses due to friction, which is delta H, but I don't know how to type the delta H in this laptop now. So let me just put it as H. These are the three losses you anticipate in a pipe network. MGH is the one due to height, potential. Call this one potential. If I'm buying a pump in the market and I want to pump the water at a height of 20 meters, if I go to my pump manufacturer, I will tell him that the head difference between the source and the point of delivery is 20 meters head. So that's already will give me an idea that I'm looking for something in the range of 2 bars. But that does not apply to submersible pump. That applies to surface pumps, right? Then, if I'm going to move to a distance of, let's say, another 50 meters, then I will now calculate again the resistance of the pipe for that 50 meters. That is the one we call H. That's the frictional losses in the pipe. Then this 2GH is now the losses due to the velocity change. We call it, what do you call it again? The fluid mechanism. There's a name we call it the fluid mechanism. Momentum change in the fluid, that's a word. They call it momentum change in the fluid. So a pipe that is moving through a fluid, a pipe carrying a fluid, is undergoing three losses. Losses due to the height difference, losses due to the moving fluid through its interaction with itself and the body, and then losses due to the frictional retardation coming from the pipe. So when you are sizing your pipe, your pump, you must overcome these three factors. That is why, even if you tell me that the head difference between the higher elevation and lowest elevation is 20 meters, if I go to the market, I might ask the market man to give me a pump head with 25 meters. Value that will take care of horizontal losses. Now, this will not make sense to you now, but as we go on, yeah, Engineer Joseph Duncan say 10 meters column of water is equal to 10 bars. Yes, that's it. I'm glad somebody have collaborated that. Okay, any other question? Today is the introductory class. So what I'm going to do next is just to run through the study materials and background in civil engineering. As long as your background is engineering, you are capable to do this. You can do it. All you need to do is to get trained. Now, I'm going to run through chapter 1 to chapter 8 so that I will know that day one, we have been able to establish a baseline, right? So that if somebody says, this is 10 years I left school, this is 20 years I left school, this is 30 years I left school, let me refresh their mind about everything they need to know about water. So if you have downloaded the materials, I would like you to go to chapter 1. There are 8 chapters. I'm going to go through them in the next 1 hour. I'm going to run at a speed. Why I'm going to run at a speed is that I expect you, between now and next Saturday, you can find time and study them, right? So that when we come next Saturday, we'll do case study. Then the thoughts start today will just be application. So let me go to chapter 1 now. Any question while I look for my chapter 1? So chapter 1, what is the course objective? I've explained all these things. It's for us to understand the fundamentals structure of a centralized water supply system, understanding of the hydraulic systems, yeah, understanding of the functions and structures of single elements of the centralized water supply systems. And finally, for us to have the ability to plan, design, and calculate a centralized water supply system and its single elements. So this is a sample of a clean water. This is a well, and this is an intake structure of a dam. This is an example of some things you see within the water sector. On the right is a reservoir. You know, reservoir can be ground reservoir, underground reservoir, or elevated reservoir. On your right is a pumping station, a big pumping station where you have two pumps. The next one is a clarifier or an aerator. I don't call it a clarifier or an aerator. This is where you put when you are doing water treatment. This thing helps to provide a larger surface for oxygen to oxidize any impurity in the water. Now, what some of us must know is this: when you talk about water treatment or wastewater treatment, the basic principle behind it is the lack of the oxidation. If you see a dirty water now and it's smelly, what it simply means is that that water does not have adequate oxygen. So if you want to treat that water, what you need to do is to put in oxygen inside it. So whether it's a treatment plant or water treatment plant, oxygen plays a huge role in treating the water. And we all know that oxygen constitutes about 3% of the air. So if you pass through air through the water, it will absorb those oxygen inside the air and release the other gases for you. So what you have on your left is a filtration bed, right? This is a filtration bed. What happens is that water comes in here and the dirty ones falls into this trough. So what are the components of a centralized water supply system? There are 5 of them: collection system, transport system, treatment system, storage system, and distribution system. Today we are focusing on the distribution system, but then there's meant to be a collection, which is like a water source. So here you see water source. You collect the raw water through the raw water intake, right? Take it to a mini treatment plant and aerate it a little bit. Then from there, you transmit it through the transmission pipeline to the storage reservoir. Right? Then from there, it goes to the distribution system. What do you need water for in a whole day? The average human being needs about 3 to 10 liters of water. For preparing food, washing dishes, each person needs about 15 to 25 liters. Flushing toilets, you have it. Irrigation, you have it. So at the end of the day, when you have done your calculation, we expect you to get between 100 and 150 liters per day. So most times we'll come and tell people the drinking water standard is 150 liters or 120 liters or 100 liters per day. The question now is, how did you get about that? This is how we got about it, by analyzing the water requirements. Okay. So this diagram is showing you the relationship between water availability and number of deaths in Germany. So all these other ones, I will not go through them. If you go through them, you understand them, right? Advantages of, like for instance, I would say impurities found in water can be microorganism, chemical substance, acidic material. All these ones, I really understand them. So that's all. Any question? Chapter 1 is gone. Okay, so chapter 2. Stay back with the overview of the water supply system. Then these are the sources of water. Depending on your source of water, you should know how to collect them and treat them. Long distance water supply does not need any treatment, so you just store it and distribute. Surface water can come in 6 different forms. It can be rainwater, it can be treated water, it can be treated sewage, and so on and so forth. So all you need to do is to collect them into an intake structure. Intake. Then if you are looking at recharge groundwater, you first of all ask yourself, is it a recharge groundwater or a natural groundwater? Irrespective of what it is, there's also need for you to build a collection system. And from the collection system, you know the end solution. Okay, like this one says, stored groundwater. Stored groundwater need infiltration gallery to pull it out. And after infiltration gallery, it goes to treatment. Okay. So if you want to select water, these are the consideration you do. The first consideration for selecting water source is what is the quality of the water. You can't compromise on the quality. Then the next one is you design the quantity. How long will it stay before it dries up? Is there enough yield? And the third one is economics of extraction. How do I extract it? Right? It's one thing for you to dig a borehole at 300 meters. And when they ask you to buy a pump of 3 bars, it becomes a problem for you. Right? So if it's groundwater, you ask yourself whether it's a groundwater with multiple formation, with groundwater with water level, with free water level, or is an artisan well. Artisan well is just like the other one that ran away. Okay, so in doing all these other ones, I think we can read and understand them. But worthy of note is the fact that a good material should have a coefficient of permeability in the range of 10-2 to 10-2. So it has to be very, very small. So we can read all this and we can understand them, right? About groundwater hydraulics, Darcy's laws and all those things. They're not too necessary. But these diagrams will make sense for you to see how this is a conventional tube well, what we know as a borehole. This is how it's constructed. And these are the ones they normally use, they perforate it and then keep it. I want to see the one that looks like a village one. So I think we can read all this and understand. Every other time beyond this place is something you can really understand. It's not complicated at all. Right? So if you still have any question, raise your hand or you let me know. So I'm going to chapter 3 now. Water consumption, right? In a provided area actually delivers and measure water. Water demand is the estimation of the water requires to be delivered. So the consumption is what they have delivered and measured. While water demand is the estimation of water quantities to be supplied, to be delivered in an area of supply. And then water demand calculation is to forecast of the water consumption in an exactly defined way of supply. So you can see if it's a consumer, different users, you need to factor in their water demand users. Somebody mentioned about industries. I think the best thing you have to size for industry is to ask yourself what the industry is producing. What is their production capacity? From there, you can estimate the number of water they need in a month. So these are some of the factors that influences water consumption, right? Please, let's have a deal. Anyone I know you can really understand, I'll just leave it. So here is showing you the impact of water when the distance to get them is high. You can see that there's less water consumption if the consumer has to take a distance to go and get it. Okay. So here, I just want us to get familiar with some of these terms. Okay, QDM is the average specific demand, the yearly thing. Q maximum is the specific daily demand. So here, this is the demand Q in liters per liters per capita per day. So the maximum peak factor, this F is known as the maximum peak factor, right? For daily peak factor and maximum hourly peak factor. What we're trying to learn here is that for every design you're going to do, you're going to impute safety factor. You're going to put in safety factor. So even after you have gotten your discharge, you still have to multiply it by safety factor to take care of all other unforeseen circumstances or any other unforeseen outcome. So these are an example of the peak factor. We'll still come to all these ones, right? Depending on what you're designing. Here are the water consumption of different subgroups. In a hospital, for instance, they expect them to consume between 120 liters and 830 liters, right? In schools, they expect to consume only 0.06 meter cube. If you convert this into liters, that will give you about 6 liters. So for a school, if you're designing for a school, you shouldn't go and allocate them 100 liters, 120 liters per cup. No, it is just school. So school is about 6. Why? Because what you do in school is to maybe go for toilet and then wash your hand. You don't cook, you don't bathe, you don't wash. So school will have a very low population. Then the next one is administration. The next one is hotel, agri farms. So these are all for you, and these are the standards. So you can reference them anytime. This 1.5 is 1.5 liters, and so on and so forth. So depending on what you're designing for, you need to include a design period. If you're designing a pump, you should know that the pump does not last for more than 5 to 10 years. So after 5 to 10 years, you must replace it, right? Then if you're designing for wells, buildings, treatment plants, storage tanks, you should not design them to last more than 15 years, 10 to 15 years. If you're not designing for water tower, don't design pipeline, water distribution. Yeah, okay. Then for dams, storage facilities, you will design for about 30, you expect it to last for 30 to 40 years. So this is the population formula you use to estimate the growth. Remember what we said, you're not designing for today, you're designing for the future. So the parameters you use is the parameters of the future, right? There are different growth formulas. The arithmetic growth, the exponential growth, and declining growth. So you choose the one that represents the subgroup you are designing for. I know that most people use arithmetic. So you can see it here. a different population growth. So nothing much here. That's end. So chapter 4. So the same thing, the same system, same water supply systems. That's what you see there. So selecting a water supply system, you have to look into account the aspect of responsibility of water supply, and economic situation of people to be supplied, local situation, available water sources, then safeguard of supply. So these are the things you must consider as a consultant, right? Who is responsible for water supply? Then what's the economic situation? So that at the end of the day, can they pay? After investing money, can you pay? Then what are the local situation? What are the local situation? What do you have? Are they using flush toilets? Are they using pit latrines? Are they farmers? Do they have gardens? What are their water use characteristics? And the next thing is, do they have available water supply? I'm sorry, available water source? Do they have spring? Do they have river water, surface water? Do they have groundwater? Then how safe is the supply? How safe? You don't sink a borehole in your neighbor's compound, right? If you quarrel tomorrow, you will seal off the borehole. So all those kind of things, you need to consider it. So you can see all the other things that I expect us to read and understand. So this is talking about rainwater. And so here, I would like to discuss the two types of water supply systems. We have the pressure systems and the gravity system. The gravity system is the system whereby this is water source through the intake. It goes to a treatment plant. From treatment plant, the water goes to a pumping station. From pumping station, the water goes to storage reservoir. And from storage reservoir, the water goes to this. That system is called the gravity system. And I can tell you, 95% of water supply systems all over the world are using gravity system. But there are another system we call pressure systems, whereby you're going to have your pump running steadily. So in that case, there's no need for pumping station. Rather, you just have inline pumps. So the pump will provide that pressure health difference. So what I've discovered is that in places like this, where you have such a thing, the system will be airtight. So once you open your tap, it will trigger the pump will come on, and then supply you with water. I did an audit for a hotel in Abuja, and I discovered that they don't have a limited tank. And I told the management that they should provide a limited tank. If not, each time a client opens a hotel in his room, the pump will come up. So what we discovered that the pump is almost running 24 hours. And that is consuming a lot of power. And we recommended that they should get a elevated tank. Because the advantage of elevated tank is that you save energy. You save, by saving energy, you save cost. So here you just pump water from this pumping station into this storage reservoir. And from there, it goes to the consumers. So this is an example of a public water supply company, right? They are supplying water to 14 communities. And for that 14 communities, total number of inhabitants is about 120 inhabitants. To achieve this, they have 14 groundwater wells, right? Not just one, not two, but 14 to service 120 people. They have 4 treatment plants, 14 wells to extract water from. They also have 4 treatment plants. And then they also have 35 storage tanks. You can see some of the storage tanks over here. And then the total length of their pipe is about 200 kilometers. What is their water source? They use both local resources and long distance water. So that is just an example. Then this is another example of another company that supplies water in the south part of Germany called Baden-Württemberg, right? And the water source is from what they call Bodensee, which is the Lake Constance. Lake Constance is somewhere, if you're going to Europe, as soon as you exit Africa, descending towards Europe, you see where they have these big mountains, okay? They call them the Alps, these long mountains. So in between there, they have this lake that is a little bit safe-guided. So that is their water source. So this water company is servicing 320 communities, making about 4 million inhabitants. The daily water demand is about 360 liters, 360 cubic meter per day. The maximum, the peak water demand is 531. So that goes back to what I taught us before. So this is the water demand and this is the peak. The difference between these two is the peak factor, what we call the peak factor. And what is the peak factor? The peak factor is like a safety factor we have in engineering, whereby what the peak factor is that when you're doing your design and you got something like say 100 naira, you don't go and tell your client to pay you 100 naira, you tend to pay you 120 naira. Why have we done that? So that if you go to the market and price of things have changed, you don't have to go back to him now to request for more money. So in all our sector in engineering, we always have this safety factor that we put to guide us and to make up for any eventuality, or to make up for error, or to make up for water losses, right? But in water reticulation, we call it peak factor. The word peak is a general word that shows the peak of something, the highest, the worst case scenario of something. Like in water distribution, in water demand, there are two peak periods, the morning peak period and the evening peak period. If you notice, those of us, when we're in universities, once it's 7 o'clock, almost all the taps will stop running water, or only they'll be running very slow. Why? Because many people are looking for the water at that point. So you see hostel A, hostel B, hostel C are all having water. So the pressure will drop. That's why you see those days in school, if you remember, if you want to go for any early morning lecture, you have to go around 4 o'clock or 5 o'clock to get water. But I know that those things are consequence of wrong design or inadequate design, right? Yeah, those bad experiences we had during our university days is lack of is as a result of improper design. Because the person that designed that network should have asked the university, because when he did that network, probably it was only hostel 1 and hostel 2. So he used, let's say, 50 mm pipe. Then the university now got TEF fund, they got funding from TEF fund. They decided to build 2 other hostels. And then the vice chancellor, who is not an engineer, will just say, there's already a water tank. Just put extra pipe to hostel C and D. When you do that, at peak period, only the original hostel A and B will see water. Hostel C and D will not see water. Unless you create a new tank for them and then a new borehole, maybe, right? But if you are now using the existing one that was not designed for them, that is where you now have challenge. So a good designer will add a peak factor and said, yes, I'm designing for hostel A and B, but I believe in the future, they are going to build hostel C and D. Therefore, instead of designing a tank of 500 cubic meter, I'm going to design a tank of 1,000 cubic meter. If he has done that, if in the future the university build 2 extra hostels, their water tank will still service them. That is why there's meant to be proper planning in infrastructure. You must plan for the future. You must plan for the new development. You must plan for change of land use. You must plan for every eventuality. And the factor that will help you to do that is what we call the peak factor. So back to what we are saying, this industry has 1 lake. They have only 1 treatment plant. They have 29 storage tanks, and their total network is about 1,700 kilometers of transmission pipes. California. In California, what they did is that they went to the Gulf of Mexico, which is a very evil thing they did anyway. I don't want to go into that, right? Because after they, if you know US, California is a very problematic area when it comes to water. They don't have water. That is a challenge for them. So what they did was to go to somewhere at the Gulf of Mexico, and they got water. They now pipe it inland using a canal. So sometimes if the community does not have water, it can actually go thousands of kilometers or hundreds of kilometers, take water and bring it inland. But what they did this time, in order to save money and also to treat it along the way, they used something like a trapezoidal member, okay, which of course also suffer from losses somehow. But when it now gets to the final destination, they will now start the treatment. Because if you treat from source, it might get contaminated by the time it gets to point of usage. Also, even if you use a closed pipe, losses might be much. So if there are meant to be losses, let the losses be when the water is not yet treated. Because there's a certain amount of money that you spend treating 1 cubic meter of water. So treated water are not meant to be wasted. Untreated water, you can afford to waste them. But treated ones already have an economic value. And if you waste them, you suffer losses. And that is why the reform in the water sector is trying to include private sector participation. So far, you don't see private sectors participating in water projects, except for at very mini scale, where people can dig borehole and then sell to public. But for someone to go and set up a treatment plant, say, I want to supply this area water, and they'll pay me back. Such thing does not exist yet, because the framework is not yet in place to enable that construct. Okay, we are done with chapter 4, sorry. So we'll go to chapter 5. I think we are making progress. So all I'm rushing this is just to explain the naughty areas, right? I expect you to go home and study them before the next class, so you have a proper knowledge or kind of background knowledge of what we're talking about. Okay, now, primary design. So basic principle of design, first of all, you do your primary design, then you do your final design. It's very important. I say technical excellence has to work, right? In other words, it must give everybody water in the right quantity, quality, and pressure. These are 3 key parameters you must fulfill in designing the water reticulation systems. It must have quality, it must be of the right quantity, and it must come with the right pressure. Okay? Then the other thing is that to maximize it, it must be protected, right? And there are 2 types of systems: gravity systems or pressure systems. Okay? So you protect the water, you're advised to use a gravity system, and then maybe you can use a loop distribution system. I'll explain all these things very soon. So part of how you do it for water is that you must protect your water source. To minimize health risk, you also might have to disinfect the water through using oxone or chlorine, which has been banned anyway. Nobody's using chlorine again because so it's suspected to be carcinogenic. Sorry, it was asbestos that is carcinogenic. Then your water must be far away from sewers, and it must be tight. Okay. So let's continue. How do you minimize costs? You minimize length of pipe, minimize number of pressure zones, because the more pressure zones you have, the more water tank you provide. Then minimize treatment. That's why I said groundwater is the best. Then minimize pumping. Minimize pumping, you have to make use of the gravity or topography of the area, except where impossible. So we've talked about this, the planning steps and everything, right? The planning steps is you can have the calculation of water demand. To do that, you do into zoning the boundaries and everything. You talk about the household, you talk about the industry, you talk about the agriculture and everything, that you calculate all these things. You understand this? Then you choose your choice of system. What kind of system do I want to use? Is it a pump system? Is it a gravity system? Right? And so on and so forth. Then the next, you determine the location of your elevated tank and pump storage station. The elevated tank is usually at the highest point. Elevated tank is usually at the highest point. Don't put the elevated tank at the lowest point. You are shooting yourself in the foot. So you have to put your tank at the highest point in the area so that will give it extra head. Then there are two distribution systems. There's a branch system and there's a loop system. The branch system is that system where everything branches off, right? While a loop system is that one or two places are looped together so that if water is not flowing in one direction, it will flow the other direction. I don't know, and I will explain this thing in the course of this training. So we're done with chapter 5. Chapter 6 is like a foundation. So we've discussed this before. We'll discuss this again, right? Okay, so here it's talking about pump, centrifugal pumps and everything. I think this one is talking about, this is the horizontal type. Okay, this is a submersible pump used in borehole. And they have horizontal and vertical shafts. So this is usually how you rate a motor, the revolution per minute or the head, suction head, or the speed of the motor. Okay, so why do you need a pumping station? For it to be a pumping station, it must have 2 or more heads. Not when you have one pump, you say it's a pumping station. No, it must have 2, one on, one off, in case of maintenance. Okay, the pumping station must have a flow guard. It must have a rough flux stopper. So booster station, this is how it looks like. You know, can just really understand. So this is what I'm trying to explain to you. The hydraulics for pumping, right? H, the losses in a hydraulic network comes from 3 places: from the geodetic height loss, the height due to the height loss due to the loss is due to the velocity, and the height loss due to the frictional of the pipe, the frictional factor of the pipe, right? So sometimes we eliminate the one due to the velocity and just limit it to the geodetic one and the other one. So in hydraulics, this is the universal, someone talked about pump. This is the universal formula to rate your pump using power. This thing also applies to power generation. You see this formula here? It can use vice versa, right? Can use interchangeably. Now, if you want to estimate the power of rating of a pump or of a turbine, it's simply a function of the manometric head multiplied by the discharge, multiplied by the acceleration due to gravity, divide by 1. This divide by 1,000 is to convert it from watts to kilowatts. This N is the efficiency. So with this formula now, I can know the power rating I need for my pump. Or with this formula, I can know the power that a stream that has a discharge Q and that can fall from a forehead of H will generate this quantity of power. Please take note of this. It's a universal thing. So this is head, as I said. Then here, what we call pump curve. Pump curve, if I remember, is like a chart or a table that shows the behavior of a pump over a period of time. Because this is what pump does. If you want a bigger discharge, your head will reduce. If you increase your head, the discharge will reduce. That is one thing. That's why if you go to buy pump, the pump manufacturer or the pump seller will give you a range of head that the pump can operate and range of discharge that the pump can deliver. So you now calibrate it. So that point where the operating point is not that point where the head and the flow has been maximized. That is what you see here. Okay, that becomes your pump curve. That becomes the operating point of the curve. Remember thermodynamics. So sometimes you design for a water reticulation system, and there's need for you to introduce two pumps. There's a need for you to have more head or more discharge. Now listen to this. If you want to increase the head you are getting from your pump, right? What you do is to put those pumps in series. If you put pump in series, you increase the head. If you put pumps in parallel, the head will remain the same, but the discharge will increase. So you need to know to say, what am I looking for? If you're looking to increase your discharge, get extra pump and put them in parallels. You get extra discharge. But if you want to get extra head, then you put those pumps in series. So there's series connection and there's parallel connection, just like we have another thermodynamic topics. So the arrangement of pump in parallel means you are looking for more discharge, or the head will remain the same. If you put pump in series, it means you are looking for more head, while the discharge remains the same. Is that understood? I suppose so. So this is just what I explained to us about pressure zoning, right? About pressure zoning.
Sorry, before we move away from here, I think about 4 slides away, the one that talks about the pressure metric head or something like that, incising the pump. Is it the same head you were talking about?
Yes.
Yes.
If you make it the subject of the formula, yeah, the same head, it's manometric head. Is the head difference just the head? Like this one, if it's a hydropower station, for instance, you know, when you want to build a hydropower station, there must be head. There must be way to turn. You know, is the head, that head that will turn the turbine, that force, that MGH, right? That potential, that's what will turn the turbine. So if the bigger the head, the more faster it will turn the turbine, and that will be the higher the current generated, just as well as the discharge, the water that is coming. We will still get to where you... Go ahead.
Yeah. The one that looks like a N, I don't know what to call it. Is there a chart to pick that?
Efficiency.
Is there a chart to pick that?
Sorry?
Is there a chart to pick that?
Yeah, there is. But efficiency is between 0.9 and 0.99, depending on the label, right? But the manufacturer, the original premium manufacturer will tell you the efficiency. And that efficiency you see there is efficiency of the motor turbine generator. Yeah. When you see efficiency of something being a certain value, it is the summation of the whole efficiency of the individual component of that system. I should go on. Okay, we're done with chapter 6.
Yeah.
are going, well, I think we are meeting up. In the next 5 minutes, 10 minutes should be done. Chapter 7. I think we still have chapter 9. So here, nothing much. Okay, I've explained this before. Function of elevated storage tank. What the elevated storage tank does is to equalize the difference between the inflow and outflow. Now, what do we mean by this? If you are pumping water into a storage tank, it might take it 1 hour or 2 hours, the pump will full. Now, you off the pump, people will start using the water. At some point, the pump needs to come back again. And even while you are doing the pumping, some waters are being used. So what storage tank does is to equalize the difference between inflow and actual demand. So the excess stays in the tank. The second thing is that you provide water and pressure in case of breakdown of the inflow. Once in case your submersible pump has issue, if you have pumped water in the tank enough, you can use it while you do your repairs. Then having water in the storage tank provide almost nearly constant pressure in the network because the water is coming from a particular place. So you have already designed it to say this water is coming from a head of say 6 meters. Therefore, I'll be having something like 6 bars and 6 bars in my network, and so on and so forth. Then types of storage tanks. Then also storage tank also provide water in case of fire. In case of fire, you don't need to go and start pumping from groundwater. You already just go from the water tank and take water and quench the fire while the fire service comes. So you have types of elevated tank, surface water, it can be elevated water tank. So there's what we call service pressure. We have minimum service pressure and maximum service pressure. I have discussed this maximum service pressure. I say it's 80, it is 8 bars. Now, the minimum service pressure is also 2 bars, right? 20. So this is where things are done properly anyway. If you are designing a network, your pressure in your system must not be less than 2 bars. That's the German standard, right? If it's less than 2 bars, maybe the water will not flow as expected. Water might be flowing so slow, or the water might not reach the whole consumers. With 20 bars, you are good to go. But then you should not exceed 80. So there won't be pipe burst. There won't be water bubbles in the tank that will cause crustation, right? And there won't be too much friction. Okay. So here, we say that minimum service pressure is the required minimum difference between minimum water level in the tank and supreme point in the community, or the point of discharge, right? Minimum pressure service point is about 20 or 2 bars. And then for every story you added, you put 5 meters. Let me explain what this thing also means. It means if you come to a community and you want to do a water design for them, you must look for the person at the highest point. That will become your reference. Because if the highest person can get water, then the person at the lowest point will definitely get water. So the highest person is the priority, because if the highest person cannot get water, or your water storage water tank is lower than his house, then you need to provide pump for him. So maximum service pressure must be less or equal to 80 meters of water, or 8 bars, as we said. So level of storage tank. So for a storage tank is the service pressure minus minimum pressure, minimum service pressure minus the reservoir head minus the head losses head. That is how to get your pressures on board. Let's not worry ourselves about this, right? Storage volume. We talk about storage tank, now storage volume. Storage volume is made up of 3 parameters. The first one is equalization volume. Just like we said, that storage tanks are meant to provide us with equalizing the inputs and the outputs, the intake and the incoming. So now here, if you want to get the total size of tank you need, you have to add the equalizing volume you add emergency volume, then you add volume for firefighting. Okay, so you can see water for firefighting can be between 48 and 340, depending on the number of hours you want to fight the fire. You know, when we say firefighting, does not mean you're going to fight the fire and quench the fire, but it's just that you can sustain the fire until fire service comes, either for 1 hour or for 2 hours. Now, this is an example of a consumption pattern, what we call consumption pattern in Germany. What I want to show you in this is that for the blue line, it shows residential area. Because you see that it peaks around 5 o'clock and comes down around 8, 9 o'clock. And then picks up again around 12 and comes down around 2. And then finally picks up around 8. So this is the typical residential area, because during this period, people are leaving for work. From 0 to 6, 5, they are sleeping. They wake up, everybody's going to take his bath. So there's pressure in the system. Peak demand, consumption will go up. Then after a while, they'll go to work. Consumption will go down. During the afternoon, they come for school runs. They need to drink water, they need to bathe water, and so on. The peak goes up again. It comes down. Then finally, around 8 o'clock, 9 o'clock, when they are cooking or whatever, the peak goes up. So, but if you look at other ones, like these red ones, it does not go that way. Okay? So some of these residential areas are different. So here, this is what we call consumption pattern. This is the water consumption pattern. This is 24 hours in a day. So people are drinking water, it's adding up, it's adding up, it's adding up until it reaches the volume of water that all of them need, which is 200. So here, what do we see here? Look at that design consumption pattern. Yeah, no. This is that consumption pattern we have. You will now just oppose it with real demand. You will see the difference. That difference is the size of your tank. That difference, because during this period, the water, anywhere you see the thing go up, it means that the consumption is bigger than demand. But in all these places, the consumption is less. That's why the green line is under the blue line. While the blue line is just consuming, it just produces, sorry. So here, the biggest inflow between this one and this one is about 170. So that becomes the size of your tank for the equalizing volume. So all these are something I think we can really understand. This is an example. Can read this, understand it, of a layout. The same thing applies here. Here, you take water, put it on storage elevation 1. If you are to supply this water to this person here, he will get the water at excess of 8 bar, because the hydraulic grid line, the energy grid line is telling you that between here and here is already 8 bars. So what you do is you break it by providing break tank. So this tank you see here is the water will supply these people, which is at the same 5 to 6 bar. But when it gets here, it cuts it off. And then here becomes like 0. So if not, if you start from here to go here, to be about 11 bars, which is beyond standard. So all this, you just have to have knowledge. So we're done with chapter 7. We are now on chapter 8. That's where we'll end for today. If we didn't do chapter 9, I think I'll just request us to read it up. Okay, chapter 8. We'll not do chapter 8 now, we'll do chapter 8 tomorrow, because chapter 8 is calculation, right? How to calculate a distribution network. After we have done our demand distribution, demand calculation, and everything, Let me see what is in chapter 9. Okay, same thing. Okay, water source. This is an example of a branch system. You can see everywhere is branching out. Why this is an example of a loop system? You can see everywhere is loop out. It's looped together. Okay, so these are the lifespan of materials that can be found in the water distribution network. So you can read all of this, you can understand it. Here is trying to explain to you the basics of pressure lines. From Bernoulli equation, you can see this is gravity loss, velocity loss, height loss, and Z loss. So H1 equals to this and this. It's not too much there. So these are the probable roughness coefficients of different materials. I think I've thought about it. We have the nomogram also. So this place is talking about nominal design. I think we'll do it tomorrow. We'll do it by next week. Here, if you don't want to do the calculation, you just want to design pipe. If you design your flow and you got 6, then know that's 100 mm pipe. We'll take it. If you get 10 liters per second, it's 125 diameter. So any value that you see here, and you ask here, you know whether right? Okay. Dimension price. I think we'll discuss all this yesterday. Tomorrow we're doing the calculation. So all these ones is in chapter 8 also, and so on and so forth. Right. So the only chapter we didn't do now is chapter 8, which we do to be the foundation of our next class. But I want to encourage us, if you get back within the week, try and study this chapter 8, right? Try and study this chapter 8. I'm going to include so far that I have their numbers. I'm going to add us to our WhatsApp group. But that will be from next week, not now. I'll create a WhatsApp group. I have a WhatsApp group for cohort 1. Let me decide whether to add all of us to that cohort 1 or create our own cohort. So, gentlemen, that is the end of the class introduction. You have the materials. You have something to read, chapter 8. Go and study chapter 8. So, like, ask me a question on Saturday. That will be our basis of our training on Saturday. I don't know if there's any question in the next 5 minutes before we end the class. Did you understand what I taught you today about cloud and now about water reticulation system? I also have shared the timetable with us. I've shared the timetable with us, so let me know if there's any challenge or if there's any problem. Anyone?
Hello.
Okay. All right. So now I'm going to end the class. I don't want to overshoot 6 o'clock because it's weekend and we have other things to do. So thank you, everyone. So we have done water demand, population projection, water collection systems. We've done, in fact, we have done most things self we're going to do. Only that the day 2, we're going to do the practical aspect of it, right? So we've done introduction to water storage, hydraulics, demand, understanding the water transmission network and everything. So like overshoot already, but it's just in foundational format. I didn't come to analyze any of them. I just rushed through them, and with the expectation that when we come next week, we'll start off from chapter 8. Any question?
Yes, hello.
Somebody say, where's the difference for the graphs? Are they relevant to Nigerian codes? Yes, it is. Okay, let me say this. Those nomogram charts are universal. In fact, they are from the University of every university, just like interest table. You can see them everywhere. They are all calibrated. It's the one I'm using for sewer and stormwater. That one is from US Federal Highway Administration, right? So these are just like charts that have been calibrated and have been proven. So they're applicable to Nigerian code. When we come to sewer, you also see them in the highway manual. Any other question?
Hello.
Yeah, I can hear you.
Yeah, so I came in late.
Okay.
Yeah, and then you said we're going to have the materials. How do we go about that?
Okay. Okay. I've done it before. Okay, let me quickly send the materials on the cloud. I think I've done that before. So I just have to do it again. So let me once again just share my screen. So I go to cloud, say copy. There you are.
Okay, so we're going to get them in our emails.
Go to chat. Go to chat box now. You copy the materials, the folder. You download everything. And that's why I said everyone should have a Gmail and a cloud account.
Okay.
Was that cloud lesson did it add value? Does it make sense to some of us? The cloud tutorial I gave us when we started. I hope it does. Okay, my last announcement is that few minutes before this class, I sent out a Google link to all the people that have registered, that indicated interest, not necessarily those that are paid. So please, if peradventure you are yet to pay for this training, I would like you to make your payment before the next class. It's very important, so that my next class I'll do a roll call for those who have paid and those who have not paid. So make sure you have paid your payment, and if there's any challenge, any issue, you can reach out to me, and I will attend to it. So in the absence of any other question, no reaction, no question, I want to thank every one of us. Okay, I've seen, okay. Yeah, please, if you know you've not copied the material, can you go now and download it? Okay, the timetable I've put up the timetable. Let me put it up again. Okay, so the timetable is in the chat box also. Please download these things. Download all these things, and I suspect I'll also send us the email. I'll also send us the email, the material via our email. Any feedback, any critique? Somebody says, I still can't see it. That's strange. Okay, I'll send the timetable to our emails. I'll send the timetable to our emails. I think that will help solve a lot of things. Any other question? Can we call it a day? You can unmute yourself, please.
Sorry, I just want to ask, sir.
Yeah.
This link that helps us to get to the documents, when you're offline, can we still have access to them?
You are going to have it indefinitely, sir. That's why I said try and get a Gmail.
Once we just click on the link, as long as I'm online, I can have access to them.
Yes, yes.
All right,
yes.
Thanks.
It's been there for like 2 years.
Okay.
No, it's been there like 1 year. Not we started this INFRAWorks today this year. But other materials we have online have been there for years.
Okay, all right.
Yeah.
Thanks.
Yeah, and if you have a Gmail, it makes it easy for you to have access to it. Okay. So I'm going to end the class now. Thank you everyone for coming. Thank you for your patience, and and trust and confidence. As I said, this training is something we are doing to add value. Sharing these materials and everything, I believe if you go through them, you're going to